introducing Chris Rapier, who is a research scientist at the Pittsburgh Supercomputing Center, which is part of Carnegie Mellon University, where he's been working on high-performance networking questions for the last 29 years. So, fun fact, one of the responses to our NANOG surveys, which please do your surveys, $100 gift card for every day's worth of surveys. One of the responses to our surveys asked us for a presentation on high-speed SSH transfers, and I said, I know a guy. So Chris is going to be attempting to show you that he is as sharp as his name, and if you have talked to him at all so far this conference, you know that he really, 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 really wants to tell you about his research.
Hi. As she said, my name is Chris Rapier. I am a staff scientist at the Pittsburgh Supercomputing Center. And I've spent the past 29 years trying to make things go faster, more securely. It took me probably 2 decades to realize that all of my work was really focused on how do I get data off of one file system and throw it across the country or throw it across the room to just reach another system. So I have done a lot of work in file systems. I've done work in TCP stacks. I've done work in network applications. And this has always been the undergirding foundation of what I do is how do I make this faster and better for the people that depend on me and depend on PSC and users in general. And I think one of the things that is interesting is how the scale has changed. When I started at PSC in '96, the big issue that we were having wasn't, the big issue we were having is how do we move hundreds of megabytes across the country? Then it became hundreds of gigabytes, and now it's hundreds of terabytes, and now we're in the process where we're moving petabytes. And each time we get that growth, a lot of times we have to try and answer the question of how do we move large amounts of data. We have to re-answer that all over again. And it's just true, bulk data transfer is hard. Getting that amount of data to the places where it needs to be in a time frame that makes sense both for business and research is a difficult question. And a lot of people have attempted to do answers for that. There are some really great applications out there called Globus, rclone, S3 buckets, FTP. All of these things exist to answer this question of how to move the data. But each of those comes with problems. Globus is now having licensing issues that makes it more restrictive for some universities to use. It's more complicated for end users. One of the other things that happen is not everyone is going to be able to use the solution you think they should use. I deal with a lot of researchers at underserved and under-resourced institutions, and they're using the cheapest thing they can get. And the options we think they should use aren't really the best ones for them. And it turns out the default, the lowest level denominator for all of this is going to be SSH. SSH is available on every single OS that you can think of, and it comes installed by default. It's not always fast, it's not always great, but it's there, it's ubiquitous, and there's a lot of value for that. It's also a lot of value that a lot of people know how to use it. You don't have to teach them new methodologies to use SSH. A lot of them just know from prior exposure. The big problem is when you're moving large amounts of data, especially large data sets, genomic data sets, confocal imaging data sets, astronomical data sets. They're huge, and SSH is just too slow for that to be a valid transfer method. And that impacts everything that uses SSH as a transport layer, and that would include SCP, SFTP, rsync, and other tools that use that as a basis. In fact, it is so slow that its use is actively discouraged by a lot of people. I was at a conference last year, and it was an interesting presentation where the guy spent maybe 5 minutes talking about how crappy SSH is. And I'm like, but wait, you don't know about what I do. So why is SSH so slow? There's a little bit of background behind it. I'm sure a lot of you guys are familiar with how important right-sizing TCP receive buffers are. Now, the receive buffer is basically the core of network flow control at the TCP layer. It regulates how much data the sender is allowed to send before it must pause and wait for an acknowledgement from the receiver. Ideally, that buffer, the amount of data that you can just accept on the receive side without doing an acknowledgement, should be equal to what's called the bandwidth delay product, which is the bandwidth at the narrowest point in the path multiplied by the RTT. And that is an expression of, rough, mostly accurate, of how much data you can have outstanding between the two hosts. And your goal is to have your TCP receive buffer be equal to that size, as you can only send one buffer's worth of data per round trip time. If that buffer is undersized, you end up with decreased network utilization across that path, and that means you have a slower transfer. So why is that a problem with SSH? I mean, in TCP, we have automated receive buffers that automatically tune things to near optimal conditions, and you don't even have to poke at anything, so it's great. So why is SSH having this problem? SSH has an application layer receive buffer to do internal flow control to SSH, and it is limited to a maximum size of 2 megabytes. Which means that SSH will only take 2 megabytes of data per round trip time before it forces the other end to pause and wait for an acknowledgement. Which means that the effective receive window of any SSH connection is the minimum of these two. So you can have a perfectly tuned TCP stack, and then you can have an SSH receive window that's 20 times too small. Why does it have this? Well, it's because SSH is a multiplex protocol. You have one TCP connection that is carrying multiple data channels. Anytime you start SSH, you're going to have an inbound channel and an outbound channel, and each of these channels has their own encryption keys on it, so it's not the same encryption going there and coming back. That means each channel also needs its own flow control. That's where that 2 megabyte limit comes in. And if you use SFTP, it has another flow control mechanism on there. It gets to the point where its flow control mechanisms all the way down. And that complexity leads to a place where you can get some less than stellar performance, like that. This graph shows how fast you can go with SSH in a sub-millisecond network. This is a 10 gig test bed. We're getting pretty decent performance, 6 gigabits on some of the ciphers. But once we hit 50 milliseconds, or 100 milliseconds, or 150 milliseconds, performance drops through the roof. It makes it impossible for us to use SSH and SSH tools like rsync to transfer data over the WAN. And that's unfortunate because SSH is a pretty good protocol, and it's widely available, and it's easy to use, so it sounds like it would be a win if we could fix that problem. Well, that wasn't as dramatic as I hoped. I fixed that problem. Using HPN-SSH, I have been able to right-size the internal SSH buffers to meet the TCP receive buffers, and so I can get you not quite line rate because we're still doing encryption, but on a 150 millisecond path, I can get you 5.5, 6 gigabits with full encryption. I can get you, and I can make that standard across a wide range of different path lengths and different RTTs. So you can actually get decent performance with all the advantages of SSH, just because I actually modified the receive buffers. Now, so what is HPN-SSH? I'm going to go into a bit more about it in detail. We're a soft fork of OpenSSH. We build on the expertise of the OpenSSH team. What we do is we rely on their expertise, and then I put my own expertise in terms of performance tuning on top of that. Every time OpenSSH does a new release, we have a new release inside of a week 2 weeks at the maximum once we do the testing and the review cycle. The primary benefit you get is by normalizing the SSH receive buffers. That just eliminated a huge bottleneck in SSH, which let us realize there were other bottlenecks within SSH that we could now address. One of them we dealt with is we parallelized some of the ciphers that are being used. So we can throw multiple threads at the encryption and decryption process and remove that out of being a bottleneck. I also do a lot of network analysis and performance analysis. So I have in-band TCP stack metrics. We have the ability to resume failed transfers when you're using SCP. So if you're transferring a huge amount of data with SCP and it fails halfway through, we can start up where it left off. We have additional enhancements that I'll be mentioning in a moment. Now, what's really important with HPN-SSH is compatibility. It needs to work with everything that's already out there. We need to work with OpenSSH. We need to work with Dropbear. We need to work with SSH.com's implementation. Any SSH version 2 compliant server or client we can interoperate with. What's even better is when we're working with these other implementations, like say OpenSSH, we still get performance benefits. The bottleneck is on the receiver side, not on the sender. So if you say you install an HPN-SSH server on one of your data transfer nodes, and someone is coming in with WinSCP, which is not known for speed, suddenly they're just going to get better performance, 10, 15, 20 times better performance without making any change on their end. This really reduces the total cost of deployment, and it just provides benefits to your end users without them having to make changes. Now, you always get the best possible performance when you're doing HPN to HPN, but we still provide improvements for any other SSH v2 compliant implementation out there. As I said, we follow the OpenSSH release cycle. So when they do a point release, we're usually out with a new one inside of a week to 2 weeks, depending on how long it takes us to go through the code review process. For any critical CVEs, we have a 24-hour turnaround time. So we are doing our best to provide the same level of security and support that OpenSSH provides. So let's take a look a little bit at how I do the buffer normalization. It's actually a pretty straightforward concept. I wrote a function that uses getSockOpt to find out what the receive window currently is on the OpenTCP connection that SSH established. I use that value to then force growth in the SSH channel buffer, and this value is what is sent to the sender advertising the available space on the receiver side. And then the sender just says like, oh, I can send you 64 megabytes of data over this round trip time, I'll send it. That is why we can provide performance benefits when you're using a non-HPN-SSH client. Now it sounds very simple, but of course, it was really complicated. I started working on this 20 years ago, and I'm still working on it because there's always nuances that crawl in there. This is part of the reason why it's complicated. That's the call graph just for a subset of HPN-SSH that deals with memory management and buffer handling. Any change in any one of those buffer and any one of those functions can have a ripple effect that will either cause memory utilization to explode, that will cause crashes, that will cause all sorts of other nonsense. So this is one of these things where it's like, well, how could you be spending 20 years working on this? Well, it's that. And this is the OpenSSH call graph as a whole. It's complicated. There's a lot going on. It requires constant reworking, especially because as OpenSSH improves their code, I have to make sure the code and the patches that I write to make it more performant match what they do without breaking, and sometimes they break my stuff. Not on purpose, I think, but It does happen sometimes. So buffer, removed one of the primary bottlenecks. Okay, that's great. What's our next bottleneck? Ciphers. Encrypting the data takes processing power. It can actually have a huge overhead, up to anywhere between 40 to 50% performance reduction just because you're doing encryption. Part of that is because OpenSSH is a highly, highly serial program. They don't use threads for anything. In SSH, each datagram, which is a packetized version of the data that you're reading, has to be packetized, and then it has to be moved over to the encryption process, then it has to go through this authentication process, and then it's sent out, and it can't start working on the next one until it has fully completed that process. But with the work that we did, we found that, the ciphers are actually a bottleneck when we're moving at, multi-gigabit speeds. Anyway, this is a quick rundown of how serialized this is. Some of the ciphers, those encrypt and decrypt boxes you see down there, we will spend 30 to 40% of our time in those boxes under a normal OpenSSH transfer. So anything we can do to reduce the amount of time that we're spending in those encrypt and decrypt paths is really helpful. So my idea was to take the existing ciphers and thread them, make them parallel ciphers. Now it turns out this is something that a lot of people have thought about, but no one has actually really done. Partly because they didn't do it because OpenSSL actually writes really, really optimized ciphers, most of them available in assembly, and trying to turn around and rebuild the cipher from the ground up as a threaded cipher introduces a lot of overhead when you're dealing with your thread management. So that wasn't really a good way of doing it. I also didn't want to write my own ciphers. I'm not an expert in that, and cryptography should be left to the cryptographers. But this is what a counter mode cipher looks like. This is what I mean by being embarrassingly parallel. You have the key, and this key is generated for every time you actually start the encryption process, and then you have a counter. This counter is just a numerical value that is incremented atomically for every round of encipher or decipherment that you do. So if you know the key and you know the counter, you can pre-compute any set of key data or this cryptographic data that you use to XOR against your data at any point. So I could actually say, like, here's the one that's starting at 0, and I'm also going to get the one that starts at 128. So I can pre-compute all of those keys in advance, which leads me to do, how do I make this happen? How do I use that information in terms of how counter ciphers work to create a parallel cipher? So the idea is to use existing ciphers, existing cipher methods from the OpenSSL API so that they do the heavy lifting. And also I don't want to fundamentally alter the way that OpenSSH works, because that's extra work for me while I'm actually maintaining my soft fork. So we threaded the needle on it. With our requirements, we decided that the right way to do this was to build information directly out of what OpenSSL can give us. We can get the raw keystream data from them. If I if I can go back a moment, I'll send you. And there, the raw keystream data is in those boxes labeled encrypt. P0 is the data that you want to encrypt or decrypt, and you XOR it against that block that says encrypt, and you get your ciphertext down in C0, C1, CN, things like that. If we can just get that box of that data that's in that encrypt box and put it into a cache, when we get data in, we can just pull that pre-computed data off of that cache and XOR it, and XOR tends to be a pretty fast operation. We don't have to wait for that specific block to be computed while we're having the data packetized and actually everything else, so we can do that in parallel. So we fill the caches with blocks of this raw keystream data. We remove from the cache for encipherment and decipherment based on where we are in the data stream, the specific block size that we're using. And we have a manager thread that refills threads as they're exhausted. We have found we can get 25, 30 gigabits of keystream data with 3 threads, which means that the cipher is no longer a bottleneck, which is pretty cool. Now, the question is, okay, you're messing with ciphers. You're messing with the encryption process. Isn't that dangerous? I'm like, yes, it can be. But we are building directly off of what OpenSSL is doing. We're not modifying any of the routines inside of OpenSSL. We're just using their expertise in a unique data structure that allows us to pre-compute the keystream data. And the result is a byte-by-byte compatible cipher implementation for both the AES counter cipher and ChaCha20. ChaCha20 is the default cipher used in OpenSSH at this point. These ciphers are also fully compliant with any other protocol compliant implementation of these ciphers. I can have one end that is doing parallel ciphers and the other end is doing serial ciphers, and it works fine. It is entirely compatible. One of the nice things is I like giving stuff away for free. So the AES counter cipher I implemented is what's known as an OpenSSL 3 provider, which means it's a autonomous block of code that you can incorporate into your own applications and call through, I think, 3 different calls. And it's really straightforward, and it's just a new cipher that's available to you if you're using OpenSSL as a library. And so this can be integrated into existing projects without that much hassle. We'll be doing that with ChaCha20 soon. Funding is always an issue, and time is an issue, and we are waiting to get one of those until we make that next step with ChaCha20. Now, here's where it gets controversial. I'm of the opinion that you do not always need to encrypt your data. There is data out there that is public. It is not sensitive. It's just internal to your own network. It's just data. And if someone captures or copies that data, there's no actual financial, legal, or technical loss if that happens. If you can turn off the encryption, then that's great. You save a lot of time. But you don't want to turn off encryption from when you're authenticating. Your authentication has to be cryptographically secure because that's just a security hole you could drive a truck through. So what we do is we created a methodology where you can have a fully encrypted authentication, cryptographically secure authentication, and then you immediately move over to what we call the none cipher or a null cipher that simply sends a date, whatever data it comes in, it sends it right back out. And this has to happen between 2 HPN-SSH installations. It does not work with any other SSH implementation for obvious reasons. So let's do a quick recap so I can show you what that looks like. This is same idea as the first graph, but in this case, we're actually grouping them by cipher as opposed to round trip time. So the big blue bar is sub-millisecond round trip time, and then it immediately drops off to 50 milliseconds, 100 milliseconds, 150 milliseconds. And that's a kind of performance that you'll actually see with the various ciphers that we have available on a standard OpenSSH. Now here's HPN-SSH. The 2 graphs, the 2 bundles of bars on the far right-hand side are how fast you can get with none, with the none cipher, and what's called the none max cipher, where we also turn off the message authentication cipher. If your need for speed is immediate, we can get you 9.5 gigabits per second, up to 50 millisecond round trip time, and we're still moving at 8 gigabits per second at 100 millisecond round trip time. I don't suggest everyone uses it, but it is an option for people who feel the need for something like this. Move a little faster through some of this stuff. This part's important to me because I did a lot of work inside of the TCP stack when I was working with Linux development, Linux kernel development. There is a structure inside of the socket called the TCP info struct that actually has a lot of instruments about what's happening inside of the stack. It gives you data on loss, retransmits, pacing rate if you're using BBR, the round trip time, out of order packets, all the sort of stuff that network engineers really want when they're trying to diagnose a problem. Now, a lot of times you can get that information off of a TCP dump, or Wireshark capture, but the problem at that point is by the time you're actually doing that capture, the problem might have been transient. It might be specific to the workflow that is happening. So being able to get some of that information in context of real-world workflows is really functional. And we can gather this information from both the local TCP stack and the remote TCP stack. So we can get you information from both ends of the connection. I know that's really small. That's just an example of the data we get. It's the number of instruments we have depends on which version of the kernel you're using, whether you're using Linux, BSD. We do not support the OS X kernel because they just rewrote everything in weird ways and I don't like it. What else? This is some recent stuff we've been working on. We have implemented multipath TCP as a connection methodology for HPN-SSH. This is really helpful for if you're on a mobile device and you're roaming between networks. This will allow you to maintain that connection as you roam from one network to the other. It also allows for link aggregation, which can in some cases improve performance. It is a runtime option. It's not the default. Because it's somewhat experimental at this point, we do not have a lot of real-world data. And a couple more versions will probably make it the default once we have the data to support that. We also just implemented RFC 8305, which is known as Happy Eyeballs. That's commonly used in web browsers to find the most optimal path between an IPv6 host and an IPv4 host if you're in a dual stack environment. What this basically does is it sets up a race. It opens two connections, one using IPv6 and one using IPv4. Whoever responds first is the connection that you're going to use. We favor IPv6 by giving it a 250 millisecond head start. The benefit of this is if you are in a dual stack environment, sometimes one of the stacks, one of the deployments might be a little flaky at times. With HPN-SSH, it will find the one that works. This is not fully implemented. It meets most of RFC 8305, but not all of it, but it is functional. This again is a runtime option and still to be considered somewhat experimental at this point. I've got 2 minutes, so I'm going to do this real fast because this is a big part of what I wanted to get to. Okay. I can get you 6 gigabits fully encrypted. That's not enough for some people. They want to be able to saturate a 40 gig pipe. They want to be able to saturate as much of a 100 gig pipe as possible. The only way to really do that is parallelization. And not only does that give you the additive increase of each stream, it's actually more stable. So if you have 10 parallel transfers, each one doing 1 gigabit per second, and one of those has a loss event and drops back into slow start, it's not nearly as impactful as if you have a single 10 gigabit stream and it drops back down into slow start. So this provides some performance security and keeps you spending more time in a place where you're transferring data faster and more effectively. We do that with this tool called Parsync FP2. It's a parallel rsync. You point it at a directory. It creates file lists based on what's in that directory, and then it fires up a farm of rsyncs that you can modify, that you can say use HPN-SSH with that, and it will automatically move your data using rsync. And with that, in real world tests, we have gotten 20 gigabits per second sustained. So it's really functional, really useful. I can talk to you more about that later. Examples, we're moving 1.5 petabytes of confocal imaging data per month from Boston to Pittsburgh. We got 15 gigabits sustained over a period of 10 days. We have corporate use cases. If any of you are familiar with a company called rsync.net, their entire business model is built off of HPN-SSH. We have other people that are using it as an RDP switch to provide HIPAA-compliant sessions for telemedicine. Last things, I'm going to have to skip these. We have a lot of information up on the website, so please come and take a look at those. Here's the website. Easiest thing to do is just go to hpnssh.org. It will point you to all of the information that you're looking for. We also have a lot of binary package, every flavor of Fedora that's supported by Coper, Ubuntu, Debian, Alpine, Arch. Come find us. Thank you, and I'm sorry I went over.
We can take maybe one question. Oh, perfect. Stay.
I will answer your question. Yes, ma'am.
Hi, I'm Sergey Masayedov, no affiliation. I hope you are aware of the SSH3 project.
Yes, I am.
That's SSH over quick. Also, the project has stalled a bit. Don't you think there could be some interesting ideas?
Yes, actually doing SSH over quick is something that we have independently started looking at doing before I heard about SSH3. It is something that I haven't had the time to actually do a deep dive into SSH v3 yet, but I do think there's going to be some really valuable stuff in there that we can use to help support the SSH v3 project and also use it with HPN-SSH. I think Quick is a great protocol, especially if we can get rid of the receive buffer issues. I think that will just be a phenomenal way of moving forward and really making an even more valuable product.
Great. Good luck with it.
Thank you so much.